First of all, I want to thank to Mr. Tibor Hegedűs that because he invited me here to be with you. My presentation it's about and first of all I want to present me because my name is Cristian Danescu. I'm from Astronomical Institute of Romanian Academy, AIRA. This is the acronym. And this is a project started 3 years ago with a friend of mine, which is Mark Rushton, a colleague of mine from the Institute, regarding a very interesting star, which is called T Corona Borealis. First part, it's a presentation of the object to understand why this is so important and why it's a very interesting star to study. This star, it's a double star actually. It's a system made by a red giant here, and a white dwarf. The red giant, even if it's very big, it have a mass smaller than Sun, about 0.8 to 0.9 solar masses, and this white dwarf, it's around 1.3 solar masses, which is bigger than the Sun, and because of this difference, the white dwarf attract mass from the red giant through an accretion disk like this. And in time, a lot of mass from the red giant came inside the white dwarf, and at some point, a nuclear reaction occurred in the upper side of the white dwarf, and an explosion happens. This is what most of novae works. But this is not an explosion so powerful that destroys the system. Those kind of explosions are supernovae, which destroy everything, and nothing remains after that. Perhaps a black hole or something like this, but no, it's not the case here. Okay, this is the place where it's located. This star near this is Corona Borealis, Alpha Corona Borealis. This is very close to Epsilon Corona Borealis. This star have a very interesting story because it was observed very long time ago, and first scientific observation was made in 1866 when it was first time discovered as a nova explosion. These are the astronomers from UK, from England, which made the observation. And the second very well documented explosion was in 1946, right after the Second World War, when a Russian, apparently Russian astronomer discovered this explosion. The English said they find it first, but I think this is the real discoverer of this nova after the war. This was the first nova spectroscopically observed, and it's very interesting that, as you can see, it's a recurrence of 80 years between this. And if you go back in time, we have another explosion in 1787, which was not studied from the scientific point of view, but it was observed by the astronomers. And it was some study made by Brad Sheffer, which is a very interesting astronomer from UK, which studied this nova. And he goes back in time and sees some documents made by astronomers from 1217, which said that in that particular area of sky, some new star occur. Some could say that it could be a coincidence, or that could be a comet or something like this, but no, because the comets were associated with bad things, with bad events that will come, but with disease or something. and on the documents of the time, this was a moment of happy. So this wasn't a comet for sure, and because of the vicinity of and the zone, the area where it was discovered is very likely to be the same nova. And if you make the steps, you'll see it's very close to this 80 years. So this is very important because because of this we could make some forecast of what is going on. So this is the photometric observation made in 1866. As you can see, it was only visual observation, so everything was in V band, if you want to say like that. And you can see it's a very high peak and very short. It's around 2 days in the brightest part of the graph, starting from magnitude 10 to magnitude 2. And then quite fast going down, and then this is the question's status of linearity, let's say, between the two explosions. But when camera was used and the photometric filters start to be used, we have this graph here, which is actually the graph from the light coming from the white dwarf, which is more energetic and emit light in more in UV or to the blue band. And as you can see, the magnitude is smaller because the star is smaller. But this is very interesting because we have a very interesting behavior. As you can see, most of the time they go together, but at some point, near to the explosion, we have here a small outburst of light in B band, okay, which goes up and then before explosion goes down again, and then it's the explosion. This is practically is the observation made in 1946. This is how it looks, the graph from that point. After this explosion, very interesting. In the second phase, it's a second eruption. I will see right away. It's a second eruption, not so much, not so big like this one, but it's here, and then status, high level energy status until the moment the energy from the white dwarf goes down again for almost 8 years to the next explosion. So now we are here, okay, and the observation, photometric observation made this nowadays shows that we are here, which is very, very similar with this instance of the graphic. So we are very near to another explosion. So this is the graph from 1946 in V and B, and from 1866, which, as you can see, they are very, very close and very similar. Again, the same behavior here, 1866 and 1946 in 2 bands. And this is very interesting, as you can see, a close-up on the graph, which is showing to us this mysterious dip from the B band before the explosion. This graph was the one from, as you can see here, 1945, 1946. So we are here now. This is the state of quiescence. I mean, we have some variation of this star, which show us this is a system, a double system of stars, and we have an orbital period of 227 days. This is this show us this graph. Okay, I spoke about this. This is the photometric observation again. Show us in BNB and making the color index, which is B minus V. We see that it will increase, which show us that we are again in the period before the explosion, the big explosion. This is a spectroscopic observation, but not to this side, but we hope to obtain something similar. It's another novae, Ares of Fuchs. Show the graph of spectroscopy in different wavelengths, in different time series. Okay, there are time series, and this is the graph. And you can see here how some spectral lines evolve in time. We hope to obtain something like this. I put it this because now spectroscopy is not very interesting. It's very static, showing us the spectra of the red giant, which is a class M3 star. So it's not something interesting to see. Okay, so we start the campaign. First of all, I want to tell you that everything, all the setup, it's in my backyard observatory. It's not from the institute. Everything it's my own stuff. And when I started this project 3 years ago, we discussed a lot about this, and we think we said what we can do with my observatory setup, again here, and find a project that could fit to small telescopes and to be again very interesting from the scientific point of view. So the setup, I will explain each and every piece. Starting, this was in 1.5 years ago. It was SkyArcher LQ6 mount, which is an old mount, so it wasn't so powerful. It wasn't so good for what we intend to do. I swapped with this one, which was much better. It's an harmonics drive mount or strain wave, which it's a new improvement, a very powerful type of mount and very precise. It's the next generation actually of the mounts after this mechanical mounts. But this one proved to have some weakness, and I go to SkyArcher 150, which is the actual mount I own, and I'm very pleased with this because it have a very high, what is the name of this? It could carry a lot of weight, actually until 25 kilos. And it's very, on the other hand, it is not very heavy. It have only 5.5 kilograms. So it's very good mount and very precise. The telescopes. This is the telescope I had before, and I have it right now, which is extremely good for astrophotography because it's completely flat field, and it have no distortion on all the field of view. But I'll tell you a little bit later why I didn't use this, and I prefer to try this one. This is a refractor. I still have it, and it's used in this survey. This was a telescope on Schmidt-Cassegrain. I had it from a friend of mine for a while, but I decided it's not very good. And this is what I have right now. It's a Richie Chrétien 20 centimeter diameter, which is the best option for, especially for spectroscopy. This it will be used for spectroscopy. And the reason I'll tell you now, because why I prefer this one instead of this one. This have a corrector plate in front. It's a plate of glass, very thick, and as you know, perhaps the glass and the atmosphere absorb very much of UV and B light. So during the explosion, the outburst of the nova, we have a lot of B light or UV light from the white dwarf. So we need to observe that one. So if you have a glass in the front of the telescope, we lost a lot of signal. So this is the reason the reflectors, pure reflectors, are preferred, like this one. Of course, a Newtonian, it will be better, but the Newtonian, the spectroscope has some limitation with the focal length, the focal ratio. You cannot put a spectroscope to a telescope with a rapid telescope with, let's say, f4 focal ratio type. This is f8, so it's exactly the camera. The cameras, again, it was a quest, searching for cameras. This is what I have. This is what I have again. This is what I have, and this one. It's on somewhere in the middle. I make some tests to see which work best. So these are the graphs with spectral. With the spectral, not resolution, spectral. I don't find the word right now. Sorry. Sensitivity of the camera. Okay, if you see, these are MOS camera, and this one too. This is a CCD camera. CMOS camera have sensitivity toward B, which is good from our point of view. I told you before why. This is perfect because it's very oriented to the B and V side of the spectrum. This is a CCD camera, very good, very good. But as you can see, it's the point, middle point is somewhere in the red, yellow, red. So at the end, I decided to use these two cameras, and you'll see how I did that. Spectroscopy, because this campaign use both sides of the scientific research, I mean photometry and spectroscopy in parallel. This is a very small spectroscope. It's actually a grating without slit in the front. This could be used in the first stages to see, because it don't have a very high resolution. Actually, it's low resolution spectroscope. It's good just to see if occurs some difference from time to time before the eruptions. This is the real stuff. This is a spectroscope made by me. It's an open project. It's a project made by Cristian Danescu, a French astronomer and engineer, and it's called UVEX. It's a 3D printed project, as you can see. Optical parts are both from American company called Tor Labs. There are two spherical mirror here, the grating, and the cylindrical lens here. And this is everything we have. And of course, in the front we have a slit. This is how it looks like. And I made here a small, let's say, automation because the slit, it's interesting. It's like a revolver slit. It have 6 positions with different slit thickness, and you cannot take everything down, strip down, and move the slit manually and then put it to work again. So I needed to make something to do this on the run, when everything works. With this automation here, we could do this very precise from one position to other. It worked quite well. It was proved, so it's perfect. The second spectroscope I made, because I make 2. This is again a project of Cristian Danescu. It's a classic spectroscope. Usually, this spectroscope was developed for the sun observation, like a spectroheliograph. It's called that's why it's called Solex. But in time they added this module for guiding, and now it could be used for star as well. So I have both of them. So when the time will come, I'll see which work best for our project. These are some of the parts from the setup. I mean, it's a computer dedicated for astronomy. This one, it's an Eagle. Controller for focuser, and for other stuff from the observatory, I can open the roof automatically. I could open the flat fill panel automatically, so everything is controlled by this controller. Okay, and now it's again about the spectroscopy. These are some, it's called starters. The old kind of this tube, neon tube, started with these starters, which produce an arc and allow to the tube to start lighting. But this technique is not used anymore right now. You have here this is the starter, okay, there or there, and you cannot find this stuff anymore. So it was a very hard quest to find these starters, especially this one, Relco SC480, which was very well documented. And why this? Because I have a calibration lamp for spectroscopy made by Bader, but it have only neon lines. Or neon lines are on the red part of the spectrum, from here to here. Not more. This is the last, or this is the last line of neon. And as I told you before, we have lines, many lines here, which are very interesting for us. So this lamp have neon and argon both. So this is the spectrum, well documented for this kind of Relco starters. I found it in Spain. I waited a long time to arrive to my place, and I took 25 to have it a whole full box, because if this is the last time when you can buy something like this, to be sure to have enough in the future as well. Okay, I stripped down the Relco lamps. This is the lid with 4 lamps on it. And this is the telescope, but I should show you. This is how it looks, my setup right now, okay? This is the refractor with the filter wheel with photometric filters. I'll show you again. This is one of the spectroscopes on the big telescope, and this is the other one on the small telescope, which I use to study the sun. But when the time will come, I'll do it for the star as well. So this is why I need that spectral lamp I show you, because we have with this spectroscope we have that spectroscope UVEX, we have a very low range of lines. We don't know where are we. We could be here, or we could be here, or we could be here, or everywhere in the spectrum. But having this calibration lamp, we could find very well and very quickly where we are, and calibrate the spectrum, and to see what we are following with the setup. This is the interconnection diagram of everything. So as you can see, this is this observatory with roll-off controlled by the computer. This is the mount. This is the Arduino Meteo station. 5 minutes. Yeah, okay. I don't think I could finish in 5 minutes, but anyway. And this is the, let's say, the software we used to control everything. The software, everything is under a SCOM standard. This is the computer which control everything, and this is where the data are going. Raw data go via RSpec. It's a software made by an American for spectroscopic data, and Tycho for photometric data. This is the, as I told you, the photometric observation. This is the filter well, and we have here V-band, B-band. This is the star analyzer I showed before. It's a grating, but it have only 1.25 inch diameter, so I made an adapter here. And I put another filter I'll show you right away. But till then I'll show this one. These are the field of view. This is the field of view for photometry with the refractor, which is huge, is big. The camera have a big sensor, and this is what we have. With the Ricci-Chrétien, which have a very, it's f.8 focal ratio, the field of view is very small. This will create problem when we try to make spectroscopy, because we need a very good pinpoint astrometry, and you cannot make pinpoint astrometry very well on small fields of view. We need more stars, or we have very few stars here in the field, and it will be a problem. We'll see how this way it will fix. It was a very interesting seminar 1 week ago made by Cheliac spectroscope company from France, which they raised the problem of exactly to do this automation in spectroscopic observation, and all the guys from there had the same problem like this one. So now we have a little bit many instruments to deal with. Okay, this is photometric observation. This is the map. We have there a map of the zone of, and some stars from EAV, so use it as a comparison star. As you can see on this image, not even calibrated. This is the star. It's very tiny, very small, 8 to 10 magnitudes. Now it's perhaps it's 10 magnitudes, so because it's in the descendant part of the graph. As you can see, there are a lot of big stars around, but this is what they are interested in. This one, the small one. And for photometric observation, we need to make calibration first of all, and this it's used we used for this Landor star. This is a list of Landor star. I already acquired images, but I use this already. It's a cluster of stars, and I prefer this because there are a lot of standard stars inside this cluster, and it's very easy to work with. This is but I don't have time, so I passed very fast. This is the formula I used to calibrate the observation and the instrumental magnitude you obtain with your own instrument and your own camera against the standard magnitude, which is what all the astronomers should obtain in the final. So to do this, to delete this bias between your own observation and the real observation, you need some coefficient, some transformation coefficient, which okay. So I did this, okay. To have a good spectra now, about the spectroscopy, I'll go very fast. I make some observations because the spectral lines should be also very well calibrated, and this is a total different type of workflow. We need to use Vega, which is a very powerful star, and it have a very powerful line, absorption line H beta, and using that line you could calibrate what you have as a spectroscope, and again to put all together and to have to obtain the resolution of your system and to fit with the standard astronomical instrument. You need to do this, which is actually I started from this, which it's very small and it's not very and I finish with this one, which is totally different. So you see, you cannot see this, but here on the final graph you see. This is a spectral a spectra of a star similar with this one, type M32, which is the red giant. But as I told you, these are titanium oxide line, but they are not interesting for the moment. So this is not. This is acquisition log for spectroscopy I used, and I have very just few slides if you allow me to finish everything. So till now we have almost 160, 70 gigabytes of data, which is huge. Because each and every night, starting from April until now, last observation night was on 29th of September, we have observation of 50 seconds in V and 200 seconds in B line, B filter. And why is that? Because we intended, and we spoke with Mark to do this, to have very dense observations in case the eruption occur, which is the big win of this campaign. Then we could see and study the period when everything will increase. No one until now never observed this. No one. It will be a first ever, which is, and due to the fact it's made with the small setup I showed you before, and it's not by big telescope. I think it's quite a very interesting thing. You could read here. This is the why are very interesting in this. We need to answer to this question. What is the unique nature of high state around the eruption, before and after? What is the natural pre-eruption dip when the graph of from B filter goes down? And the most important, the spectroscopy after the explosion will show you if we have some neon lines, because neon lines show us that this is a precursor of supernova type 1A, which it's again something we don't know for the moment. So this will tell you if somewhere in the future this star will become a supernova, not just a nova, a recurrent nova which explodes every 8 years. This is extremely interesting because it's what we introduced new in this campaign. We make a filter which is called, I found this, 1 minute. I found this in a forum of English astronomer. They make a compound filter made by two filter. You could usually find it very, very easy. A planetary filter number 47 and a shot glass B39. And put this together. This is the planetary and this is the shot glass. I put it together. It's very simple. It's not any science rockets. What is interesting about this is we obtain a filter very close to a photometric filter, but between B and between U. It's something like this. This is the graph, which is much better than B. Of course, we don't have some calibration data to have similar observation with others. But after the eruption of the star, we could use this with a telescope which I already obtained. It's a Newtonian F4. It's a fast Newtonian with 250 millimeters diameter, which allow us to obtain enough data, enough photons, and without any glasses, but only mirrors, to obtain something like this. I mean, a graph exposure of not more than 10 seconds, which is very hard. And in this part of the spectre, they did this to this star, V6040 Carina, which show this kind of oscillation, very short period of oscillation, which we expect to occur and to see and study when the accretion disk will start again after the eruption, 2 or 3 years, because it don't start right away, but after sometimes this will start, and the flickering.
In the active phase.
No, when everything. No, here.
Second.
Somewhere here. between this high state and the quiescent state here. When then the accretion disk will one slide. That's it. Okay. Because it's important just to have some conclusion, and that's it. These are the conclusions. So this campaign, it will resolve a lot of and will answer to numerous questions. This star have a unique pre-eruption high state and deep, unlike any nova. We don't have any nova having this behavior. Not any known nova. It's very close to us. I mean, it's 800-900 parsecs from us, which is a good distance to see a lot of variability in this star. It's a fast nova in the classification scheme of that means you need to be very quick prepared for a solution campaign, because we could lose the opportunity to study and to have information maybe in 8 years from now. It's well placed in the sky. Of course, this is very important because it's in the sky most of the year, except starting from in the month of half of November till the half of January, when it's not visible in the sky. In the rest of the year, it's up. And you could study the star very, very, very easy. I think the time is up for a long time ago. So I'm sorry about doing this, but I thought it's important to show you everything to understand why I'm so happy and so excited about this project, and why I wanted to have a good some good results in the end. The most important and most is like winning lottery. It's to capture that rising part, because that's exactly like the chemical. It could be in the moment that we can see the star in the sky. It could be cloudy. It could be not at daytime. So a lot of if, but it could be there in my sight with my